Okay, so if you're an electrician working in Alberta, there's one system where your professional liability is really front and center.
You mean fire alarm systems? Absolutely.
Exactly. These are complex networks, they're life safety critical, and, well, provincial law says you're the only trade permitted to install them.
The stakes couldn't be higher, really. We're talking about protecting lives, protecting property.
Which means everything is driven by code, right?
Oh, absolutely. Rigorous codes. Think the National Building Code, Alberta Edition, the NBC-AE, and also the ULC standards, Underwriters Laboratories of Canada. Non-negotiable stuff.
So today we're doing a deep dive into the technical material. We want to map out the tech, the requirements, basically what makes these systems reliable when things go wrong.
Yeah, looking at the systems, the components, how they operate, and those all-important regulations.
Okay, so at the most basic level, what does every fire alarm system have to do?
Two crucial things. First, it needs to identify that there is a fire.
Right, either someone pulls a handle or a device senses it automatically.
Exactly.
Yeah.
And second, it absolutely must alert the building occupants.
With sound and flashing lights, usually.
Yep, audible and visual signals, synchronized to get people moving, evacuating.
And to handle just those two jobs, the bare minimum system needs
What? Three things.
three essential pieces. You need the fire alarm control unit, that's the panel,
Yep.
then a manual pull station, and finally an audible signal device like a bell or horn.
Okay, let's start with that control panel.
Yeah.
It's not just a box with wires, is it? It's really the nerve center.
It absolutely is the brains of the operation,
Yeah.
and it has to constantly manage four distinct operating conditions. It's got to be ready to switch between them instantly.
Four conditions. Okay,
Yeah.
what's the default?
That's the normal state. System's powered up, circuits are supervised, everything's quiet, just waiting.
Waiting for trouble.
Literally. If the supervision detects any kind of fault, maybe a wiring break, a device failure, boom, you're in a troubled condition.
And trouble isn't an alarm, it's a system fault signal. Correct. It signifies an equipment issue. And critically, it has to trigger both an audible signal and a visual signal at the panel.
Why both? And why is silencing it restricted?
Well, the audible part gets your attention immediately. But the key thing for liability and safety is that the audible trouble signal can only be silenced by authorized personnel right at the panel.
Ah, so you can't just ignore a wiring problem. Someone has to physically acknowledge it.
Exactly.
Yeah.
Prevents fault from being silenced and forgotten until a real fire exposes the weakness. You have to log it, deal with it.
Makes sense. Okay, condition 3 must be the actual emergency.
That's the alarm condition. This means activation, evacuation, the horns, the strobes, they're all active
And it stays active until...
until the initiating device is cleared and safe. And then it must be manually reset by authorized personnel. It never resets itself from an alarm. Never.
Okay, normal, trouble, alarm. What's the fourth?
The supervisory condition. This one's a bit different.
I usually hear that linked to sprinkler systems, water flow maybe.
Often, yeah, but it's broader. Supervisory is proactive. It signals a change in a related life safety system, like sprinklers, that could prevent it from working correctly during a fire.
So like low water pressure. Or someone closing a valve.
Exactly. Loss of air pressure in dry system, maybe the handle on the main water supply valve has been turned, things like that. It flags a potential issue before it impacts an emergency response.
And like an alarm, it needs a manual reset once fixed.
Correct. Same procedure. Someone has to verify the system is back to normal.
So 4 complex states, all juggled by the panel's CPU, the brain.
Right, the central processor unit. And if you want to simplify its main jobs, we can kind of group them.
Okay, how would you group those 6 main functions?
Think of it as input, output, and integrity.
Input would be power coming in and receiving signals from detectors and pull stations.
Perfect. Output is then transmitting signals out to the notification appliances, the horns and strobes, and also controlling those ancillary devices like unlocking doors.
And integrity covers the self-checking.
Exactly. That's the electrical supervision constantly monitoring the circuits and providing status indication, letting you know what condition the system is in. It's doing a lot all the time.
All right, so the panel manages things, but how do the devices actually, talk to the panel? I know there are different ways.
Yeah, there are two main technology architectures.
Right.
The older style, conventional, and the more modern, addressable.
Conventional. That's the zone system.
That's the one. Devices are grouped together electrically into zones. So if a detector goes off, the panel can only tell you something like, alarm in zone 3.
Which might be the whole 3rd floor, maybe? Not very specific.
Not at all. And supervision works by sending a tiny current, maybe around 5 milliamps, through the zone wiring. If the current changes unexpectedly, it signals a trouble. It's simpler electrically, but yeah, it needs more wiring runs and gives you less info.
Okay, so contrast that with addressable systems. This sounds like where the real advances are.
Big time. Addressable devices are smart. Each one detector, pull station, module gets a unique digital address, usually set with little switches on the device itself.
Like an IP address for a fire detector?
Kind of, yeah. The panel actively polls each device, constantly asking, are you okay? Any alarms? So instead of just zone 3, the panel tells firefighters, alarm activated at device address 101.
And you know, device 101 is, say, the smoke detector in room 205.
Precisely. Cuts down response time dramatically. You go straight to the source.
That's huge. What about reliability? Faults?
Another big plus for addressable. In a conventional system, a short circuit on the zone wiring often causes an alarm condition, a false alarm.
Right, because the current changes drastically.
But in most addressable systems, a similar short circuit usually just results in a trouble condition for the affected devices on that loop. The panel knows something's wrong with the communication, but it doesn't trigger a full evacuation, much less prone to false alarms from wiring issues.
So addressable needs more setup, more programming maybe?
It does require more initial programming, yeah. But the payoff is huge flexibility. You can set different sensitivity levels for detectors, maybe less sensitive in a dusty area, more sensitive near critical equipment. You can do complex zoning for evacuation sequences in big buildings, much more powerful.
Okay, we have the brain, we have the communication network. Now let's get into the actual detection. How do we catch the fire in the first place?
Well, first, it helps to understand how a fire typically progresses. There are generally 4 stages detectors are trying to catch.
4 stages. Okay.
It starts with the incipient stage. This is where there might be invisible combustion particles, but no smoke, no flame, no real heat yet. Very specialized detectors can sometimes pick this up.
Then what? Smoke.
Usually, yeah. The smoldering stage. Now, you have visible smoke, but still maybe not much flame or significant heat rise. And this stage is really dangerous.
Why is that? Just smoke.
It's not just smoke. It's consuming oxygen and producing toxic gases, like carbon monoxide. Our source material really stresses this. If oxygen drops below about 17%, your coordination and judgment are impaired. Below 6%, breathing stops. Smoldering fires can fill a space with deadly conditions before it even gets hot.
Wow. Okay, so incipient, smoldering, then it really takes off.
Right. Stage 3 is the flame stage. Actual visible flames ignite. And finally, the high heat stage, where the fire is fully developed and heat radiation is the biggest danger, causing other things to ignite.
Got it. So our first line of defense, the simplest one, is the manual pull station.
Yep, the pull box, basic simple stage type. You pull the handle, contact's close, sends an alarm signal straight to the panel. Immediate evacuation.
But there's a 2-stage version too, isn't there?
Yes, 2-stage stations. These are vital in places like hospitals or high-rises where immediate mass evacuation might be chaotic or dangerous.
How does that work differently? Pulling the handle on a 2-stage station typically activates only an alert signal, often just in certain areas, or maybe just for staff. It signals, investigate the situation.
So not the full evacuation alarm yet?
Not yet. The second stage, the general evacuation alarm, requires a key. Trained personnel firefighters, building staff, insert a key and turn it to activate the full alarm.
What if no one responds to the alert?
Ah, good point. Code requires a failsafe. If that first stage alert isn't acknowledged or manually escalated to the second stage within 5 minutes, the system must automatically trigger the full evacuation alarm.
Okay, smart backup. Now, moving to the automatic detectors trying to catch those fire stages.
Right. They generally work on one of 3 principles: detecting heat, detecting smoke or other products of combustion, or detecting the actual radiation light from a flame.
Let's start with heat detectors. Are they common?
They are, especially in certain areas. They're generally the slowest to react, but they have a very low false alarm rate. Think places like dusty workshops, boiler rooms, kitchens, areas where smoke or steam might cause nuisance alarms with other types.
What kinds are there?
You've got fixed temperature types like fusible link detectors. A metal alloy melts at a specific temperature, breaks the circuit. Simple, reliable, but you have to replace them after they activate.
Okay. Any others?
There are also bimetal types, which use 2 metals that expand differently with heat. They bend, make contact, and trigger the alarm. The advantage is they usually reset themselves once cooled.
And rate of rise. That sounds different.
It is. Rate of rise detectors don't wait for a specific high temperature. They react to how fast the temperature is climbing. If it jumps up too quickly, say 15 degrees per minute, they signal an alarm, even if the actual room temperature is still relatively low. They give you an earlier warning of a fast-developing fire.
Interesting. Okay, moving on to the most common type, probably. Smoke detectors. Faster than heat?
Generally, yes, much faster for most common fires and better for covering larger open areas. There are two main technologies you'll encounter constantly.
Ionization and photoelectric.
Exactly. Think of ionization detectors. They have a tiny bit of radioactive material, americium-241 usually. It ionizes the air particles in a small chamber, creating a tiny electrical current.
Okay.
When smoke particles enter that chamber, they attach to the ions and reduce the current flow. The circuitry detects that drop in current and triggers the alarm.
What kind of smoke are they best at?
They're typically very good at detecting the tiny invisible particles from fast flaming fires like a paper fire catching quickly, often associated with darker smoke.
But they have a downside, false alarms.
That's their weakness. They can be easily triggered by steam from a shower, cooking fumes, even dust sometimes, so placement is critical.
Right. And the other type, photoelectric, how does that work?
Photoelectric detectors use light. There are two main ways: light scattering or light obscuration.
Lights.
Yeah, the most common type. There's a light source, usually an LED, shining a beam away from a sensor inside the detector. When smoke particles enter, they scatter the light, and some of that scattered light hits the sensor, triggering the alarm.
And light obscuration.
That's more like a beam detector. A light source shines directly onto a sensor. If smoke gets dense enough to block or significantly reduce the light hitting the sensor, it triggers.
What kind of smoke are photoelectrics better for?
They tend to be better at detecting larger smoke particles, the kind you often get from slow, smoldering fires, think a couch or mattress fire. Often associated with lighter colored smoke, they're generally less prone to false alarms from cooking or steam than ionization types.
So different detectors for different fire types, really.
Ideally, yes. That's why sometimes you see dual sensor detectors combining both technologies. Beyond those common types, you get into specialized detectors too.
Like what?
Well, duct-type smoke detectors installed in HVAC systems to shut down fans and prevent smoke spreading through the building ventilation. Very important. Or beam-type detectors for huge open spaces like atriums or warehouses. They shoot a beam of light across the space to a receiver. Smoke interrupting the beam triggers an alarm. Covers a massive area with one device pair.
And really sensitive one.
Yeah, aspirating smoke detectors. These actively suck air from the protected area through a network of pipes with tiny holes. The air sample goes to a highly sensitive detection chamber. You see these in computer rooms, data centers, clean rooms, places where even a tiny bit of incipient smoke needs very early warning.
Okay, that covers smoke and heat. What about flame detectors?
Flame detectors are the fastest reacting, but they need a direct line of sight to the flame. They're looking for specific light radiation signatures.
Different types here, too.
Three main ones based on the light spectrum they detect: infrared, IR, ultraviolet, UV, and flame imaging.
When would you use, say, UV?
UV detectors are very fast and good for detecting fires from flammable liquids or gases that burn clean, like hydrogen or methanol. Think fuel-loading docks, chemical plants.
But sensitive to other things.
Extremely. Welding arcs, arc lamps, even lightning can trigger a false alarm in a standard UV detector. You have to be really careful with placement and application.
IR.
IR detectors look for the specific infrared radiation pattern flickering flames emit. They're better in smoky or dirty environments where UV might be blocked, good for fossil fuel fires.
And flame imaging. That sounds new.
Relatively.
Mm-hmm.
These use sensors similar to a CCTV camera, often analyzing both UV and IR spectra plus the visual image. They use algorithms to look for the characteristic shape and flicker motion of a real flame, helping to differentiate it from false alarm sources like reflections or hot objects.
Yeah.
More complex, but much more reliable in tricky environments.
Okay, so a detector or pull station triggers the alarm. The panel knows what happens next. The panel starts controlling other building systems, right?
Exactly. It actuates what we call ancillary equipment.
Ancillary, meaning related, but not technically part of the fire alarm system itself.
Precisely. These are components with a direct life safety job that get activated by the fire alarm system during an emergency. They handle the physical response logistics.
Give me some examples.
Okay, door releases are common. These are typically electromagnets holding fire doors open. On alarm, the panel cuts power, the magnets release, and the doors close automatically to compartmentalize the fire and smoke.
Makes sense. What else?
Door unlocks. In secure areas, the fire alarm needs to unlock designated emergency exit doors to ensure people can get out.
Overriding security for evacuation.
Yep. Then there's HVAC control. This is crucial for smoke management. Typically, the system shuts down air supply fans to stop feeding air to the fire and spreading smoke. It might turn on exhaust fans or activate stairwell pressurization systems to keep escape routes clear.
And elevators. I know you shouldn't use them in a fire.
Right. The fire alarm system performs elevator homing or recall. It overrides the normal elevator controls and automatically sends all cabs to a predetermined floor, usually the main egress level.
So they don't get stuck between floors, and firefighters can use them if needed.
Exactly. Ensures they're out of the way for occupants and potentially available for emergency responders.
Now, does the fire department automatically get notified?
Not always, but it's mandatory in specific cases. If you have a two-stage system, or you're dealing with a large assembly occupancy, think over 300 people, you must have a fire department signal connection.
And that connection reports what? Just alarms?
Alarms and supervisory conditions. It has to notify the fire department or an approved monitoring center immediately if either an alarm or a supervisory signal is initiated. They need to know if the system is impaired, not just if it's in full alarm.
Okay. Now, alerting the occupants inside, the horns and strobes. Any specific rules there?
Oh, yes. Audible signals, bells, horns, speakers have to be synchronized if you can hear more than one from any single location. You can't have them ringing or pulsing slightly out of sync. It's confusing and less effective.
Same for the visual signals, the strobes.
Yeah. Visual signals must also be synchronized if they're within the same field of view. You don't want multiple strobes flashing randomly. It can be disorienting, especially for people sensitive to flashing lights.
And they're required in specific places.
Yes. Strobes are mandatory in areas with high background noise, where horns might not be heard clearly, or anywhere people might be wearing hearing protection, and importantly, in areas accessible to people with hearing impairments.
Is there a minimum brightness?
There is. The code specifies a minimum luminous intensity, usually 15 candelas, to ensure they're noticeable.
These strobes and horns, they draw a fair bit of power, don't they?
They draw a lot of power, especially strobes. And over long wire runs in a large building, voltage drop becomes a serious issue.
Meaning the devices at the end of the line might not get enough power to work properly.
Exactly. The voltage could drop so low that the last strobe doesn't meet that minimum 15 candela requirement, or the horn isn't loud enough. That's a code violation and a failed inspection waiting to happen.
So how do you solve that?
You use a notification appliance circuit extender panel, sometimes called a booster panel. It's essentially a separate power supply with battery backup, controlled by the main panel, that provides power locally to a group of notification appliances. It boosts the power and supervises the local circuit, overcoming the voltage drop problem on long runs.
Okay, we've got the tech, the communication, the ancillaries. Now let's nail down some of the absolute must-know rules from the code, the physics and the law, basically.
Right, because all this hardware is useless if it's not installed and configured to meet specific performance requirements set by the NBC AE and ULC. These rules ensure the system actually works in an emergency.
Let's start with sound levels. How loud does it need to be?
The audibility mandates are very clear. In general, non-sleeping areas, the sound level must be at least 65 dBA or 10 dBA above the normal ambient noise level, whichever is higher.
So, in a quiet office, 65 dBA. In a noisy workshop, it has to be 10 decibels louder than the usual machinery noise.
Precisely. It has to cut through the background noise.
But sleeping areas are different.
Significantly different. For sleeping areas like hotel rooms or apartments, the minimum is higher, 75 dBA at the pillow.
75 dBA. Why so much louder?
It's specifically intended to be loud enough to wake someone from sleep. The code recognizes that rousing a sleeping person takes a stronger stimulus.
Okay, but there must be a maximum, too. You don't want to cause hearing damage.
Correct. There's a global maximum sound level, typically 110 dBA, to prevent permanent hearing loss during an evacuation.
And the sound itself, it's not just a constant blast, is it?
No, it absolutely cannot be. The standard audible evacuation signal must be the temporal 3 pattern, often called T3.
Can you describe that?
Sure, it's a specific sequence. 3 half-second pulses of sound, followed by a 1.5-second pause. So O-in, on pause. That repeats.
And why that specific pattern?
It's been internationally researched and recognized as the distinct sound for fire evacuation. It's less likely to be confused with other building alarms like security or timers. When people hear T3, they should know it means fire, get out.
Okay, T3 pattern. Got it. Now, something that sometimes causes confusion, smoke detector versus smoke alarm. What's the difference according to code?
It's a critical distinction. A smoke detector is a component, a sensor, that's connected to and part of the building's main fire alarm system. It sends a signal back to the central control panel.
And a smoke alarm.
A smoke alarm is a self-contained unit. It has the sensor and the sounder, the alarm horn, all in one package. Think the kind you typically find in houses or individual apartment units. It operates independently or interconnected only with other smoke alarms.
Ah, okay. And for those residential smoke alarms, is there a key requirement?
Yes, a huge one for safety in dwelling units.
Mm-hmm.
Smoke alarms installed within a single house or apartment suite must be interconnected.
Meaning if one goes off.
They all go off.
Yeah.
If the smoke alarm in the basement detects smoke, the ones in the bedrooms and hallways must sound as well, ensuring everyone hears it, regardless of where the fire started.
That makes total sense. Okay, last big area, power requirements. These systems can't fail if the power goes out.
Absolutely not. They require both a reliable primary power source and a secondary or emergency power source.
Primary is usually just the main building power.
Yes, typically a 120-volt AC circuit.
Mm.
But critically, it must be a dedicated branch circuit. Nothing else allowed on that circuit.
Dedicated. Why?
To ensure its reliability. You don't want the fire alarm system losing power because someone overloaded a circuit with a vacuum cleaner or a kettle.
And the disconnect for that circuit, the breaker.
It has specific requirements, too. The breaker or disconnect switch must be clearly identified, colored red, and it has to be lockable in the on-in position.
Lockable on-in. Why?
To prevent someone from accidentally or intentionally shutting off power to the life safety system without authorization. It physically emphasizes its critical nature. Life safety power stays on-in.
Okay, primary power covered. What about the secondary emergency supply?
That's typically batteries, located in the control panel or a dedicated cabinet, or sometimes a backup generator in larger buildings. And there are strict rules for how long it needs to last.
How long is that?
The emergency power source must be able to operate the entire system in its normal supervisory state, just monitoring, no alarms active, for a full 24 hours.
24 hours? That seems like a long time.
It reflects the possibility of extended power outages during major events, storms, grid failures. Responders might not be able to get there quickly. The system needs to stay functional and supervised throughout that entire period.
And after the 24 hours of standby?
After providing that 24 hours of supervisory power, the batteries must still have enough capacity left to operate all the alarm notification appliances, horns, strobes at full load for a specified duration.
How long do the alarms need to run on battery?
That depends on the building and occupancy type. It ranges from 5 minutes for some buildings up to 2 hours for others, like hospitals, where evacuation is slow and complex. So, 24 hours standby plus full alarm operation time. That's the minimum reserve required. #tagoutro.
Wow, okay. We've really journeyed through the whole ecosystem, haven't we? From the basic 3 components of a minimal system through those 4 critical operating conditions: normal, trouble, alarm, and supervisory.
Yeah, and looking at the big shift from conventional zone systems to the precision of addressable technology, plus all those specialized detectors for heat, smoke, and flame.
So what this really means for you, the listener, the electrician installing or servicing these systems, is that every wire you connect, every device you mount, it's part of this incredibly sophisticated, highly regulated, interconnected network designed purely for life safety.
That sound of the alarm, the T3 pattern, it's not just noise, it's the voice of that entire system working as intended, based on these strict codes and technologies.
So here's something to think about, maybe mull over as you work on these systems. We talked about that dedicated primary power circuit red breaker locked on, and the crucial 24-hour plus alarm duration requirement for the secondary battery backup.
Right, absolutely critical.
Knowing the complexity of these systems and how much relies on that backup power actually being there when needed, what's the single most important procedural check beyond the basic install that you need to build into your routine, maybe during commissioning, maybe during annual service, to ensure that vital secondary power reserve isn't just calculated correctly on paper, but is functionally guaranteed to be there ready to perform on day one and, just as importantly, 5 or 10 years down the road?